Okay. Okay, so I think we'll get started. So we're very happy to have Philip Argyres talking to us all the way from Cincinnati, in the US, and he's going to tell us some things about S-duality in field theory. So Philip, thanks very much for talking to us, and over to you.
Yeah, thanks for the invitation. I mentioned to Jock that when I got the email, for a moment I was excited because I thought you were actually inviting me out there. But anyway, a little disappointed that it's only via Zoom. Someday I'll make it out.
You're always welcome. So,
so I'm going to talk about S-duality in field theory, and this will be a fairly sort of a discursive summary, even slight sort of historical tour of the notion of S-duality. So I'll emphasize what S-duality is and talk about some examples, and then focus on the by far best studied example, which is N=4 supersymmetric Yang-Mills theories. And only at the very end, I'll say a little something new, a tiny little new thing about S-duality that comes from this work with these large group of collaborators that one paper appeared a while ago and more to appear. These are not really about S-duality per se. They're much more focused on these notions of generalized symmetries, but we're trying to develop certain techniques, and the way you always start in supersymmetric field theories is you start with the N=4 super Yang-Mills theories, because those are so simple and so well understood. So that's always your first step. So so here's the outline of the talk. First, I will talk a little bit about what we mean by S-duality, and then a very, very short review of what N=4 super Yang-Mills theories are. And then I'll talk about the long history of S-duality conjectures and how they've changed and been refined over the years. And then, like I said, time permitting, at the very end, I will talk about some possible slight further refinements. So first, what is S-duality? So it's come to refer to an exact equivalence of two different field theories. And that's a really unsatisfactory way of defining it, because what that really means is you thought two things were different, but you were wrong. So it's some sort of, that way of talking about it, which is the way everybody talks about it, by the way, is kind of relies on your psychological state. So for example, a gauge theory has a theta angle, and the gauge theory with the value of theta and the different gauge theory where theta is replaced by theta plus 2 pi, they look like different Lagrangians. You might have thought that they were different theories, and you were wrong. So this would be an example of an S-duality. And of course, you don't think of it in that way. We just have internalized, since it's been 50 years, that theta angles are angles, and so we just should think of them mod 2 pi. S-duality is something similar, as I'll try to say. So maybe a slightly less psychological definition is to say that if you have two apparently different definitions of a field theory, like two different Lagrangians or something, and an S-duality is when these two apparently different definitions of the field theories give the same answer. And there's, of course, a very familiar example of this in physics, which is the notion of universality classes of field theories under RG flow, under renormalization group flow, where you can give wildly different wildly different microscopic definitions of your field theory. And if the question you're asking is what is their long distance behavior, flow to their infrared fixed point, they could have the same infrared behavior. And we would say these two are in the same universality class. We generally call those universality classes, but sometimes these are also called dualities. So for example, Seiberg dualities and four-dimensional supersymmetric gauge theories, or 3D mirror symmetry or mirror dual pairs are examples of like this. But so S-duality is a more sort of specific kind of equivalence that does not depend on RG flows. And one way of thinking about this is, let's say you have two different free quantum field theories. Why free? Because that's the way we understand most quantum field theories. We start with the free theory, and then we quantize it. And let's say that there's some parameter, like a space of couplings. That's what these pink kind of manifolds sticking out of the free quantum field theory are. So we have two spaces of quantum field theories, which I'm calling M1 and M2 here. And who knows, as you go to strong coupling, what they are. And S-duality would be the statement that these two theories, it's not so much that free quantum field theory 1 and free quantum field theory 2 are the same. It's just that they're actually connected to one another. That is to say, we would say that quantum field theory 1 and quantum field theory 2 are S-dual if they are connected in a single space, continuous space of quantum field theories. So then here's the free quantum field theory 1 is some limit, quantum field theory 2, and the idea is, we can take a path like this to this theory, and a path like this to this theory. They look different, but it turns out that they're actually the same point in this space of theories. So, so this space M, this moduli space of continuously connected field theories is really the object of study when people are talking about S-dualities. So that's what I'm just saying here. So we're studying the space of couplings of quantum field theories, generally of continuous couplings of quantum field theories. Okay, good. So this is a very high-level introduction of just the notion of S-duality. By the way, feel free to just interrupt, pipe up with questions if you have any.
Maybe can I ask a quick question about the moduli space?
Sure, yeah.
Is it clear that it's always a continuous manifold? Could there be singularities in the moduli space?
Oh, a smooth manifold. No, it's almost, I don't think we know of any examples where the geometry on this space is smooth, actually. Furthermore, it's not even a manifold, typically, that it can have various intersecting branches, so non-manifold points, and also it can have disconnected components. And that's, in fact, exactly what I'll be talking about, so to speak.
Okay, thank you.
So the cleanest setting, so that we don't have to worry about RG flows of theories and so forth, is to look at scale invariant theories, conformal field theories, so that there's no RG flow. Each point on this manifold is an inequivalent conformal field theory. In that case, this manifold has a name. It's called the conformal manifold of the theory. And often people talk, if you have a set of conformal field theories that are connected by changing a dimensionless coupling, in other words, you're just changing from one nearby conformal field theory to another one, moving on the conformal manifold. Often people now talk about this as a single conformal field theory, okay? Even though, strictly speaking, every distinct point on this conformal manifold is a distinct conformal field theory. It's just language. So this is our setting. So we want to understand the geometry of conformal manifolds of conformal field theories. Understanding this is the same thing as asking questions about the S-duality of the theory. And I'll make that more concrete. So in fact, we're going to start with two examples, which are kind of cheats, because they're really examples involving free field theories. So they're not what we're really interested in S-duality, which involves interacting conformal field theories. So let's talk about, first, let's start easy. Let's talk about two-dimensional unitary conformal field theories with central charge 1. Those are essentially theories of a single free massless scalar field phi. And it's a free theory, so what could the possible couplings be? Well, you can make the target manifold a circle. That is to say, you can identify the field and the field plus a constant. In 2 dimensions, the scalar fields are dimensionless, so this is actually a dimensionless coupling of the theory. And there's also a discrete thing you can do, which is you can gauge a Z2 symmetry, which takes phi to minus phi. Okay, and it turns out that's in some almost all the things that you can do to a free field theory, and so we have complete knowledge of the conformal manifold of these C=1 unitary conformal field theories. And it's this space in blue. It's this semi-infinite line segment, and then sticking out from a point here, another semi-infinite, another ray, and then 3 isolated points. That is the space of C=1 theories. I've taken this from the, if this is unfamiliar to you, there's this beautiful review of this by Ginsburg long ago. And this is the ray of these theories with circle target spaces, and these are the ones with circle target spaces, but you've also modded out or orbifolded, as people say, by this Z2 symmetry. And so this is the orbifold part of the moduli space, and this is the unorbifold part of the moduli space. And they're various non-trivial things. There's a point on the unorbifolded space which coincides with a point on the orbifolded space. So there's this unexpected equivalence of 2 different looking theories there. So that might be an example of an S-duality in the informal sense. But more importantly, these line segments don't go from radius, I'll call this radius, but I guess it's circumference really of the circle, of circumference 0 to infinity. It goes to a finite circumference. In a certain normalization, it's 1/√2. And the point is that the smaller compactification circles, or these target space circumferences are equivalent to larger ones. There's this sort of inversion symmetry in R. This is the thing that interchanges the momentum and winding modes of the 2-dimensional field theory on this target space. And so this would be just the sort of thing that we think of as an S-duality. In this case, it's actually called T-duality, and there's a similar sort of inversion symmetry for the orbifold case. Okay, so good. I maybe pause here just to see if there's any questions about this, but I'm trying to give a simple example of what I mean by the conformal manifold and just show that even in very simple cases, it can have quite a complicated structure. So now let's get to something closer to our eventual goal. And let's talk about 4-dimensional free Maxwell theory. So here's the familiar Lagrangian. The Maxwell Lagrangian and the theta angle, the topological term. And here are the coupling parameters. It will be convenient, right, to put them together into a single complex coupling where the theta angle is the real part and 1 over the coupling squared is the imaginary part. We'll see why in just a moment. But I should say a comment about in what sense these are couplings. In the free Maxwell theory, this is a total derivative term. So the coefficient in front of it, this whole term is irrelevant, and so theta, it doesn't affect anything. And in fact, we know E can't affect anything either, because this is just a theory of free non-interacting photons. So I could just reabsorb E into a rescaling of what I called my gauge field. So these are not actual coupling constants of this theory at all. It's just, there's just some field redefinitions which get rid of them effectively. So, but there is a sense in which I can think of these as couplings as when I think not just of free Maxwell theory, but free Maxwell theory in the presence of non-dynamical electric and magnetic sources. So I take my space-time and I cut out arbitrarily placed world lines of dyons, of electrically and magnetically charged sources. And then I talk about the response of Maxwell theory in the complement of these world lines. And then these things have a meaning. They tell me about the strength of the coupling to the lowest, the minimum charge electric and magnetic sources. To be consistent, I need so-called mutually low. I need the Dirac quantization condition between the electric and magnetic charges to be satisfied. So when you do that, the set of couplings of this theory is not the set of all these complex numbers, but it's this domain in the complex upper half plane of tau, which is the fundamental domain of a group of identifications generated by these two identifications, S and T. T is the identification of tau with tau plus 1. Well, you can see what that is. That's simply the periodicity of the theta angle that we're familiar with. And S is a little bit less obvious. Maybe I do it down here. The S generator, if I turn off the theta angle, the S generator inverts the strength of the coupling, and at the same time, it replaces electric with magnetic fields. And so this is generally called not S-duality, but electric-magnetic duality of the free Maxwell theory. And the group generated by these two transformations is famously this group of Mobius transformations of the upper half complex plane, where the coefficients A, B, C, and D form an integer determinant 1 matrix. So this is the group PSL2Z. Okay, so this is called the electric magnetic duality group, and this space here can be thought of as the conformal manifold of the free Maxwell theory in this sense. So now, so here is the kind of a Lagrangian, I don't know, algebraic definition of S-duality group as a set of identifications among what we thought were different couplings. But now let me turn it around and just say, let me just focus on the geometry of this space and use it to recover this electric magnetic duality group. So what is this space? Oops, sorry, keep on going up and down here. But this space is this infinite, almost kind of rectangle, sort of, with these two edges identified by the T transformation. So it's really like a cylinder. And at the bottom here, this bottom thing is identified by this S transformation. So this point is fixed by the S transformation, and this point is identified with this point. So if you think about it, you see that you have once you do those gluings, you have a corner, a Z2 orbifold point here, and the opening angle here and here is 2 pi over 6. So you glue them together, you have an opening angle 2 pi over 3. So you have a Z3 orbifold at this corner. And up here you have going to I infinity, you have a kind of a cusp-like point. So topologically, or at least as an orbifold space, it looks like a sphere with 3 marked points, one of which is a puncture, a cusp, and the other 2 are orbifold points. These are 2 strong coupling points in the manifold. And this is an invariant description of the conformal manifold of this theory. So how do I recover this algebraic description in terms of S-duality groups from it? Well, in this case, it's pretty easy. I just compute the fundamental group of this space. If it was simply a three-punctured sphere, I pick a base point, and the fundamental group would be generated by homotopy classes of, say, two simple loops that go around one of the punctures and the other puncture. The third one is then determined in terms of those just by, pulling them around. So it would be the group freely generated on two generators. But these are these orbifold groups. And so the idea is for a Z2 orbifold, if I go twice around this point and come back, that's a contractible loop. So this generator S, that would be this loop, satisfies the condition that S squared is to 1. And this generator U satisfies the condition that U cubed is equal to 1. So the fundamental group in the orbifold sense of the conformal manifold is this abstract group, and as an abstract group, that happens to be exactly the S-duality group, PSL2Z. So in many cases, that's how you can sort of, if you had access, in some sort of Lagrangian independent way, you had a definition or an understanding of the space of couplings of your conformal field theory, then you could recover information like the S-duality group.
Sorry, Philip, so you're saying generally, if I knew how to compute the homotopy group for the moduli space, then that would tell me something about the duality group.
It will tell you something, it wouldn't necessarily get what you might want to call the duality group on the nose. Right. There's really more these are actually metric spaces. The space of coupling of conformal field theories famously carries a metric structure, the so-called Zamolodchikov metric. It has a high dimensional analog. So there's lots of information in this space. And I just picked out in this case where the coupling space happens to be two real dimensional, one complex dimensional, it's fairly easy to just, this captures a lot of the information about the space. But if I have higher dimensional moduli conformal manifolds, then this might not capture that much. There's a lot richer data in the, you really want to, in other words, be talking about the geometry of the conformal manifold, but so I'm just giving.
Just said, yeah.
Okay, cool.
Okay, sorry, yeah.
No, don't apologize. So, so this also is not called, what I just described is not called S-duality. It's called electric-magnetic duality. In these free cases, they have their own special names. And generally, we reserve the term S-duality for interacting conformal field theories. Now, for historical reasons, sometimes some people call the S-duality of interacting N equals 4 super Yang-Mills theories, some people call that electric-magnetic duality, but they mean S-duality. I mean, most people now don't call it electric-magnetic duality. They reserve that for the free case. So like I said, the original and best studied examples of S-duality come from 4D N equals 4 super Yang-Mills. So let me now just very briefly tell you what that is. I'm not a lot of detail here, but I'll write down a partial Lagrangian. It's a Yang-Mills theory, so it has a trace F squared and a trace F wedge F term, the usual coupling and theta angle term. And it has also a set of 6 real adjoint scalar fields. These are part of the superpartners of the gauge field in N equals 4 supersymmetry. And so they have their kinetic terms and a certain potential term that arises. And then there's also fermionic partners, and then there's also Yukawa couplings, and they have their gauge kinetic terms as well. And all the fields are in the same multiplet, so they're all, in some sense, transformed in the adjoint representation of the Lie algebra defining the theory. So it's completely specified. This is a very simple theory. It has a lot of a lot of symmetry, and it's specified by our familiar complex coupling, together with a discrete choice of the gauge Lie algebra. At least as far as writing down this Lagrangian is concerned. Okay.
Sorry, Philip, can I just interrupt for a second? Just go back to the example we were just talking about. How did you know, if you didn't know anything, like I don't know anything, so how would I know to compute pi1? Like, why would, aside for just for fun on a Saturday morning or something, is there an a priori reason for thinking?
No, I'm just saying pi1 is some coordinate invariant property of the geometry of this space. That's all I'm saying. I mean,
and
a much more detailed one is the actual metric. I mean, we actually know what the metric on this space is. It's actually the one that you get from putting the constant negative curvature metric on the upper half plane and doing these identifications. Then this actually becomes a constant negative curvature space with these shown metric singularities.
Yeah.
I'm not sure I answered your question, but
well, if I think of I didn't know that pi1 would have captured this much information. Actually, I wouldn't have known what it would capture, to be honest.
Yeah. But I'm saying this is a little bit special to this two-dimensional example, two real-dimensional normal manifold. If you go to higher ones, the pi1 stops being as powerful, doesn't capture that as much information.
Yeah. Okay. Sorry.
Okay, so let me just tell you about some basic properties of n=4 super Yang-Mills that were kind of worked out in the 80s and early 90s. The first thing is it's automatically a conformal field theory. That is to say, the beta functions for these couplings vanish exactly. I mean, there's actually not quite a proof of that. It's a self-consistency argument under the assumption that supersymmetry is not spontaneously broken in these theories. But the evidence for that is just overwhelming by now. So it's about as close as a proof that you can get, given that this is an interacting field theory. So that means in particular that these are conformal field theories, and this coupling is an exactly marginal coupling. Changing it moves you from a conformal field theory to a nearby conformal field theory. But observables depend on the strength of the coupling. This is a self-interacting theory. And so correlation functions and so forth, at least in perturbation theory, you can compute, they have tau dependence. So changing the value of tau, at least typically changes the takes you to an inequivalent conformal field theory. These are conformal theories, so they don't develop mass gaps, they don't have dimensional transmutation, so they don't have any of the really difficult properties of the Yang-Mills theories, like QCD and the Standard Model. They're very well-behaved, highly symmetric, but still interacting field theories. And something which is not immediately obvious is that they have this property that they have a continuous moduli space of vacua. And they have not only a vacuum in which the conformal the scale symmetry is unbroken, but they have a continuum of vacua, they all have exactly the same energy, what's called zero energy, right? But in all the other vacua, the scale invariance is spontaneously broken. So what happens out of this on these vacua is a Higgs mechanism in which the gauge algebra is broken down to some of U1 factors, the number being equal to the rank of the gauge group. Okay, and because the low energy physics out on these vacua is just sort of our copies of Maxwell theory of electromagnetism, this is called the Coulomb branch, because the force law between the charged sources is the Coulomb law. Okay, so these are two different things. This is the conformal manifold, the space of inequivalent theories, and for each point in this conformal manifold, there is a moduli space of vacua. I'm not going to say much about this until I get to the end of this talk. It's the connection between these two things, which is the thing that I'm studying with my collaborators. But anyway, the last, yeah, is there a...
So here you wrote down the phase where you completely X the gauge group, but you could have also cases where you remain with a vacuum that still preserves some 1 billion part of the original gauge.
Oh yeah, very good. So this is the generic point on the Coulomb branch, and there are sub varieties in the Coulomb branch where you don't completely gauge down to U1 factors, and you leave, you go to the conformal point of, let's say, a subgroup. So if you were like SU3, there'd be a couple of directions in which there's an SU2 subgroup cross a U1 and so forth. So yeah, it's very interesting kind of, what's it called? Stratified structure to these moduli spaces.
Thanks.
Thanks. The last thing to say about n equals 4 super Yang-Mills theory, if you haven't played with them, is that they are by far the best studied interacting field theories, aside from a class of exactly solvable or integrable theories that exist in 2 dimensions. But in higher than 2 dimensions, by far the best studied field theories that are interacting, not free, are n equals 4 super Yang-Mills. The standard model included. I mean, there are many more papers on the standard model than there are on n equals 4 super Yang-Mills, but what we know about the standard model from all our work on it is just a tiny pittance compared to what we know about n equals 4 super Yang-Mills theories. These theories have so much symmetry and are so well behaved that we can compute things to all orders and certain perturbative expansions, and it's just amazing the amount of data that we have on n equals 4 super Yang-Mills. Some people even hold out the hope that these n equals 4 super Yang-Mills theories may be someday exactly solved. I'm not sure that there's a lot of evidence that that's going to happen, but anyway, they're that well understood. But I'm going to show you that even though they're that well understood, their S-duality properties, their geometry of their conformal manifolds is something that is still evolving in some sense. So I'm going to, how am I doing on time, by the way? Okay, go ahead. Maybe I'll speed up a little bit here. But so now I'm just going to give you a kind of informal history of S-duality conjectures. And it started, right after, but more or less right after, Tuft-Polyakov monopoles were understood and discovered. And Goddard, Neutz, and Olive, by looking at just the structure of semi-classical magnetic monopole solutions of Yang-Mills theories, found that monopole solutions are associated with representations not of the gauge algebra G, but of, oops, I don't know why it does that. Here we go. Not of the gauge algebra G, but of an associated dual gauge algebra called the GNO dual, which was also known at the time by the mathematicians and called the Langlands dual. And if I just say what the duality on the algebras are, it's not very interesting because all algebras are just dual to themselves except for this one pair. SO odd is dual to SP algebras, but all the other ones are self-dual. But that's not really the content of the GNO duality. it's really this more detailed mapping between the two, that it maps the weight and co-weight spaces of these two theories, so that the root lattice of G is isomorphic to the co-weight lattice of G dual, and vice versa. And with this data, you can actually, it implies a mapping of the global forms of the gauge groups as opposed to the Lie algebras. That's a way of actually kind of understanding what the content of these mappings are. And so let me give this long list. Actually, I don't think it even fits on the screen. Hold on, let me see if I can get it to, here we go. Here's this list of GNO gauge groups and their duals. And it's a long list. You have to look at all the different distinct global forms of these compact Lie algebras. But so I don't expect you to, digest this list, but I would like you to look at the top three entries, because they'll play a role in what follows. The first one is that if you're talking about an SUN gauge group, then the different possible global forms are SUN modulo some subgroup of the center. So in particular, if n is factorizable, so let's call it SUN times m, then there is a global form which is SUNM mod ZM. And GNO duality says that its dual partner is SUNM mod ZN. In other words, I've just exchanged the two factors, so to speak, in the center, which is Z and N. So this is kind of a basic example of GNO duality. And there's a similar, example in the SO to SP duality. And there the centers are Z2, so there's sort of two versions. There's the SO and its cover, the Z2 cover spin, and SP is the Z2 cover of SP mod Z2. And these guys are these dual pairs. Okay, so eventually, so where we're headed is that we're going to be saying that the n equals 4 super Yang-Mills theories with not just the Lie algebra, but a certain choice of the global form of the gauge group are going to be S-dual, that are going to be equivalent to ones with these dual gauge groups. So that's where we're headed, but let's see how we get there. So in that paper, of course, here they weren't thinking about supersymmetric theories or anything. The theories they had in mind were the Yang-Mills theories, and they were asymptotically free. So it was unclear what the significance of this sort of semi-classical argument was. So they made some sort of vague speculations that these theories somehow, that a given Yang-Mills theory has sort of electric sources that are defined by the gauge group and magnetic sources which are somehow feel this dual gauge group. And Montanen and Olive made a specific conjecture, and for that reason, this version of S-duality is often called Montanen-Olive duality. And they said that the gauge group G Yang-Mills and G check Yang-Mills are equivalent, and what you have to do is under just the renaming or interchange of electric with magnetic degrees of freedom, and at the same time in replacing the gauge coupling with its inverse. Very similar to electric magnetic duality of the free Maxwell theory that we talked about before, but the difference now is that the electric and magnetic states are part of the Yang-Mills theory. They're not put in as external sources here. And the evidence was a semi-classical BPS mass formula. And then right away, Witten and Olive point out that in supersymmetric theories, this BPS mass formula is actually enforced by supersymmetry to be exact. But they also point out that at least for n equals 1 super Yang-Mills theory, that the Olive-Montanen conjecture could not be true because the electrically charged states and the magnetically charged states were in different dimension multiplets. And so there couldn't possibly be a symmetry between the two, or this equivalence between the two. And then it was pointed out by Osborne that if instead you look at maximally supersymmetric super Yang-Mills, n equals 4 super Yang-Mills, then the Olive-Montanen conjecture could be true, because now the counting of the electric and magnetic states is the same. They lie in the same multiplets. Okay, so that, and so this sort of Olive-Montanen-Osborne conjecture is this, is what most people think of, I think, still to this day, as the S-duality conjecture.
Is that Hugh Osborne?
I'm sorry?
Is that Hugh Osborne?
Yes, Hugh Osborne, yeah.
Does it say to be n equal 4, or it actually works also for n equal 2?
This, in this form, only for n equals 4. Now, there is a generalization of the notion of S-duality to n equals 2, but actually, I think as I said at the very beginning of this, S-duality in a general way applies to any theory with a conformal manifold. So any set of conformal field theories with exactly marginal couplings, there's some analog of the notion of S-duality. In the end, what you're interested in is the geometry of its conformal manifold. So this has been, especially the so-called S-class n equals 2 theories give many, many examples of very interesting S-dualities in n equals 2 theories. But they don't have this kind of a simple sort of algebraic, as simple a flavor as in this Olive-Montanen-Osborne case, where it almost looks like the free Maxwell electric-magnetic duality. Okay. So, and then there's a decade of string theory, and Schwartz and Sen look at some sort of these conjectural group of identifications or dualities of 2B strings, and they're the ones who named it S-duality, I believe. And they point out that if it's true in the string theory, then by compactification, it would then imply this Osborne-Montanen-Olive duality in n equals 4 super Yang-Mills. And then a kind of a breakthrough occurs in the early 90s. Part of it is just due to the work of Seiberg and Witten having more control over exact computation of certain supersymmetry protected objects in strongly coupled quantum field theories. But to do with S-duality, Sen was able, points out that S-duality implied the existence of a certain pattern of bound states of the monopole and Dion solutions, and then he was able to actually verify some of these predictions, and that was very convincing evidence, because it's the sort of computation you do looks like it has nothing. Anyway, it's not a proof. It's a piece of evidence, but it's convincing evidence, I think. and since then, S-duality now and tied in with our belief in the equivalence of the various string theories and so forth, this whole thing is the amount of evidence in favor and supporting S-duality is now sort of overwhelming. So it's all in the form of self-consistency arguments. It's not, and so not proven. it's widely believed. So S-duality was kind of thought of as this PSL2Z group of identifications on tau, on this gauge coupling, and right away, Dory, Fraser, Hollowood, and Knight point out that when the gauge group is non-simply laced, so it's SO odd or SP or F4 or G2, that the S-duality group can't be in PSL2Z, but it's in a different kind of subgroup of discrete subgroup of PSL2R called Hecke groups. I just wanted to, well, this will play a role at the very end, but I just wanted to point that out because it's a little bit more complicated than you might have thought. This shows it. But then the real sort of breakthrough comes a decade later when Kapustin shows that, or I guess it was kind of known, but he's the one who really showed explicitly that instead of thinking about how these dynamical states, the electric charged particles and magnetically charged particles that are part of the field theory, the dynamical degrees of freedom, how they are interchanged under this S-duality equivalences. He says that we can just we can ask how the spectrum of mutually local probe line operators behaves. And these things, so this is much more actually like the free Maxwell theory, where we're putting in probe electric, non-dynamical electric and magnetic sources. And then we're saying, oh, the electric magnetic duality involves an interchange of what you're calling electric and magnetic. And so Kapustin shows that this is the action of S-duality, the identifications of S-duality on the spectrum of Wilson and 't Hooft line operators is also is a kind of a computable and sensitive test of S-duality. And so he's able to show sort of rigorously that these guys are classified by representations of the Lie algebra and the GNO dual Lie algebra with this, the whole GNO dual thing. And it takes a little while, but then these people, and especially this second paper, which is so-called reading between the lines paper, using this set of probe line operators, are able to greatly refine these Montanen, Olive, and Osborne duality predictions. And so those are the kind of the modern form of the S-duality predictions for n=4 super Yang-Mills. And it's not just a refinement, there's actual modifications. Some statements from of this original conjecture are now known to be false, and it's quite a bit more intricate than what was thought before. So let me just give you a flavor of some of the new things that were learned a decade ago. So first, a general statement is, if the Lie algebra is SUN, then there is not one conformal manifold for this theory, but there's a bunch of different conformal manifolds. So we would call them, there would be a bunch of separate SUN theories. That's maybe not surprising because the GNO, the Olive Montanen thing would have said that, well, if you have SUN, there's also SUN, say mod ZN, and these two theories would be connected. But if N had divisors, there would be other pairs that would be connected by S-duality. So you might expect that there's a bunch of different global forms of the gauge group. So what so you might think, oh, it's the total number of divisors of n divided by 2 would be the number of different disconnected components of the conformal manifold. The number of, those are, in the literature, those disconnected components are called S-duality orbits of this Yang-Mills theory. But it turns out that's not the answer. The answer instead is not the total number of divisors divided by 2, but it's just the total number of square divisors of n. So if n is a prime, there's only one square divisor, 1. But if n were 8, right, then 1 would be a square divisor, but 4 is a square divisor, because 4 is a square, is 2 squared, right? So in that case, in the case of SU8, then you'd expect 2 guys. So first, let me give it an example which matches with what we, maybe refines just what we already knew from the Olive-Montanen conjecture. Let's take the case of SU3. So there's only one orbit. There's 2 global forms of the theory, namely SU3 gauge group and SU3 mod Z3. So you might expect that there's a conformal manifold with 2 free limits. And in fact, that's what happens. The conformal manifold has 2 free limits, and it turns out it has one Z3 cusp, one strong coupling conformal field theory with an enhanced global Z3 symmetry. And furthermore, the S-duality group is a certain modular subgroup of PSL2Z. And there's an associated constant curvature metric. So we know everything about the geometry of this space for, say, SU3 n equals 4 Yang-Mills. And by saying SU3 n equals 4 Yang-Mills, there's just one conformal manifold, and that's the end. That's all you have to say to specify the theory.
And sorry, so Philip, each point inside the manifold is regarded as a distinct
is a distinct theory, and in this case, we can compute enough exact invariants, observables in these theories we have enough of them to actually show that every point is distinct, that there's no map, there can't be further identifications, because there's enough supersymmetry protected invariants that we can compute that we can tell all the points apart.
Mm. So it's just funny, because when you think of the orbit of a group, you think about the geometry that the action of the group on a point generates or something. But that's not how it's going here. So each point inside that manifold is not related to another point by S-duality.
Well, I could, of course, I could go to this tau upper half place, and then there's some funny domain here, which is the fundamental domain of this modular subgroup. And I get that space just by identifying the boundaries of this funny domain.
Yeah.
I could tile, so to speak, the whole upper half plane with multiple copies of this thing. So that's the old way, if you like. I don't know, it's the old way, I think of it as a non-invariant way of talking about the S-duality.
Yeah.
So I'm running out of time, and I want to get to the end. So I was going to point out places where you have actual disagreements with the old things. So for instance, for SU6, the number of divisors of 6 are 4. There's 1, 2, 3, and 6 divide 6. 1 and 6 would be, so SU6 and SU6 mod Z6 would have been Montanen Olive dual, and SU6 mod Z2 and SU6 mod Z3 would have been dual. And you expected those to be 2 separate theories, having their own separate conformal manifolds. But what you actually find is that they're all connected together. There's only a single SU6 theory. So there's other things. Even the number of distinct weak coupling points has to get modified. This has to do with these so-called discrete theta angles that were understood by Aharoni, Seiberg, and Tachikawa. And you get interesting cases where the we know that the space of couplings doesn't even have to be a multi-punctured sphere. You can have higher genus. There's the first example is SU11, is a 2-punctured torus, for instance. So cool.
Yeah, it's very cool.
So now I want to go and talk about this Coulomb branch of vacua, and try to figure out what the connection between the S-duality, the geometry of the conformal manifold M, and of this space of vacua. And since I'm short on time, I'll go kind of quickly through this. It's been known for a long time that as a complex geometry, this Coulomb branch of vacua has this very simple flat orbifold picture. It's just C to the 3R, where R is the rank of the gauge group, orbifolded by kind of a certain natural action of the Weyl group, which is a finite reflection, real reflection group, and you just sort of take its kind of tensor product with C3 here, so that it has a kind of a natural action on C3R. Okay. This defines a complex geometry. This is some complex space, and you give it a certain actually singular Kähler metric, I mean non-analytic Kähler metric, which is the one that's inherited from the flat metric on the space here in the numerator. But this geometry, what is it? Where does it come from? It encodes the kinetic terms, or the low energy leading terms of the effective action out on this space of vacua. And there's more structure to that low energy effective action than just its kinetic terms. Why? Because on this Coulomb branch, the low energy effective action was these R copies of Maxwell theory. And Maxwell theory has this electric magnetic duality identifications. So as you move around on this manifold, kind of looping around the points where you have this enhanced symmetry group that somebody brought up earlier in an earlier question, you have to keep track of these electric magnetic duality transformations on the low energy theory. So it's an extra structure, and that structure is encoded geometrically in a certain refinement of Kähler geometry called special Kähler geometry. So this description fails to capture the full low energy data on the theory. And somewhat surprisingly, understanding the special Kähler structure of this manifold has not been systematically studied. And that's actually what I'm doing as part of what I'm doing with these collaborators. And so I'm just going to tell you that this is an orbifold, and you have an action of this discrete group here. This is just inherited from the natural reflection group action of a Weyl group. But to specify a special Kähler structure, you need extra information about how this group acts. Namely, you need a representation of the Weyl group as a set of integer 2R by 2R symplectic matrices. Okay, and over the reals, all these representations are equivalent to the reflection representation that I was talking about, but they can nevertheless be inequivalent. There can exist inequivalent representations over the integers. So you have to do this kind of number theoretic thing of trying to figure out all the integrally inequivalent such representations of the of this Weyl group. So this is something that we've done. You try to extract it from the math literature, It's not actually completely done in the math literature, but we now know the answer to that question of how to classify all these inequivalent representations. And they are in one-to-one correspondence with all the possible Coulomb branch structures. And so up to some interesting slight subtleties, they are basically in one-to-one correspondence. The different special Kähler structures are in one-to-one correspondence with the different S-duality orbits. So when I have a theory like, let's say, the n equals 8 theory, where the theory has a conformal manifold which has two disconnected components, what we find are two distinct special Kähler structures. One corresponds to the Coulomb branches of these theories, and one corresponds to the Coulomb branches of these theories. And because they're different geometries, at least generically, it's telling us that these theories can't possibly be the same as these theories, because there's an observable, namely the low energy effective theory on the Coulomb branch, which is different in these two theories, different in this subtle way. Mm-hmm. So, so let me just point out an example of one extra interesting thing that a type of interesting thing that we see. So here I'm going to give another example, the SO5 theory. Now, which is under GNO duality, that would be dual to the SP4 theory. But it turns out that exactly at rank 2, SO5 is actually the same as SP4 as a Lie algebra. So there's not even a matter of duality. It's in some sense self-dual. But if you work it out, or as actually Aharoni, Seiberg, and Tachikawa worked it out, there are two S-duality orbits. So the conformal manifold has, the prediction is the disjoint union of these two manifolds. This one is not the fundamental domain of a modular subgroup of PSL2Z. It's actually the fundamental domain of the fourth Hecke group, something like that. That's this thing that I was mentioning before. But in any case, this geometry is completely understood, and this geometry is completely understood. But now we can, by computing for every point in here, what is the resulting geometry on the Coulomb branch, we have some sort of a great deal of extra data. We've computed for every conformal field theory here and here. We've computed this very detailed, exact, observable property of these conformal field theories, and we notice that generically, the low energy theories, the Coulomb branches of all these theories, are distinct from the Coulomb branches of all these theories, and they're all distinct from one another, except there is one special point here and one special point here where they exactly coincide, somewhat miraculously. So we can show that all these other points have to be, they cannot possibly be the same conformal field theory, because we can compute observables in them and they disagree with one another. But except for this one point, and we can compute we can go through the list of all the known properties of these two strongly coupled n equals 4 super Yang-Mills theories, and they all agree. So they have exactly the same generalized one form symmetries and the whole list. So there's a natural conjecture, which we don't know how to prove or disprove, but the conjecture is that they're actually the same theory. Mm-hmm. So the actual conformal manifold of the SO5 n equals 4 super Yang-Mills theory really has only one, it has a single connected conformal manifold. It has these sort of two components that share a point, if you like, intersect transversely at that single point.
Can I ask you a question?
Yeah.
So, it looked to me that this evidence is strongly based on a BPS observable. Do you expect that if you consider the effective action, not only the special Kähler part, but the higher derivative, whatever, this is going to remain true?
So of course, these S-duality equivalences are conjectures in the sense that we compute what we know how to compute in these theories and compare the two. But that's far, because we can't compute everything in these theories, it's far from a proof. So, there's just a sort of a kind of a web of evidence that makes us really strongly believe that this is the correct description, that the truth, that the real conformal manifold is not a double cover or triple cover of this space here. That would be the case if, as a function of tau, we look in some fundamental domain which covers this and a neighboring fundamental domain which covers another copy of it, but we computed some, say, non-supersymmetric supersymmetry protected observable and found a different answer in the corresponding points. Then we would say, oh, we were mistaken. This is not the correct conformal manifold. You actually have to go to some sort of multiple covering of this to describe all the inequivalent conformal field theories. So we strongly believe that that does not happen, but we can't prove it, right? It comes from just deducing a lot of evidence. You can compare with you can make certain computations that are not protected by supersymmetry near the weak coupling points and perturbative expansions and so forth. And there's certain in certain nice situations, and especially, that you can then you can show some appropriate that they satisfy some relations that you expect from S-duality. For the conjecture that I've just given here, the conjecture is that all the observables of these two theories coincide, even the non-supersymmetric, supersymmetry protected ones, but we do not know how to prove that by far. This is a point stuck way inside of strong coupling. So this is some strongly coupled conformal field theory. They're far from their Lagrangian descriptions. We don't really have any good techniques for computing non-supersymmetry protected properties of these two things. So in that sense, you're right. The evidence that we have for this yellow identification is pretty weak. So that's why I call it a conjecture. But it's everything we know how to compute exactly in these two theories coincides.
So if the conjecture is true, am I supposed to think of those two domains as actually being joined?
Yeah, they touch at that point.
They touch at that point. So
you can continuously go from here to here and come out over here.
Yes. Yeah, exactly. Yeah, that's what I was just wondering. Yep. Yeah.
That would be the idea.
A bit like Reed's fantasy.
Yes.
Oh, baby example of Reed's fantasy. Yeah.
So maybe I'll end with open questions, which are the ones that are being raised here. But maybe there's one that's not obvious, which is the first one. I've talked about these n=4 superconformal theories, and I mentioned these n=4 super Yang-Mills theories. These are the ones which are connected to weak coupling points. So they had a Lagrangian description. Are those all of them? Could there possibly be n=4 superconformal field theories that have their own, moduli space of conformal manifolds, but there's no point at all that's ever weakly coupled? That's an open question. We just don't know how to get at theories like that. How do we answer for sure yes or no in a question like that? So I put that out there as a challenge, so to speak.
Yeah.
There's kind of evidence that you say, well, we have ways of hitting non-strongly coupled, non-perturbative field theories by string constructions. And if they existed, you kind of expected we should have seen them in string theory. That's not a rigorous argument, but that might be an argument that makes people think that, oh, n=4 super Yang-Mills are all the n=4 superconformal field theories. That's my gut reaction, but there's no proof. And then there's this Reed fantasy thing. What is the connectivity of all of these things? Is it true that they all actually end up getting connected? You can do, there's certain limits in which higher rank theories, you can go to limits where things become decoupled. And well, anyway, so there's certain senses in which you can ask about certain ways of writing paths between these theories. Could you get to all of the theory? Are they all in some sense connected in this way? And then much more interesting would be the n=2 analogs of all these questions. And of course, this is really where me and my collaborators are headed, is we want to understand the theories with less than n=4 supersymmetry, and to what extent can we understand general properties and detailed properties of these conformal manifolds. And there's been a lot of work over the last couple of decades on this question, but much less is known in general about the n=2 case than is known about the n=4 case. So I should end there. Thanks.
Thanks for patience. No, that was a beautiful talk, Philip. Thank you very much. Yeah, that was amazing. Any questions from anyone else?
Something? You go, Johanna.
Okay, thank you. I have a question about the special the special geometry appearing here. So I know special geometry in the context of n=2 compactification of type 2 string theory. So is there any intuition as to why the Coulomb branches, the moduli space is associated to the Coulomb branches, have special geometry and not, I don't know, a hyperkähler or something like that?
Great question. So if there was just n=2 supersymmetry in the low energy theory, there would be two sort of different kind of variety, because there's vector multiplets and hypermultiplets. You can have places where you have a massless vector multiplet out on the moduli space, and those would be the Coulomb branches, and the ones where there's only massless hypermultiplets would be Higgs branches, and those would be special Kähler and hyperkähler geometries. In the n=4 case, there's only now the vector multiplet, and it's in some sense a combination of an adjoint hypermultiplet plus the vector multiplet from the n=2 perspective. And so there's not a separate Higgs and Coulomb branch, there's a single geometry, and I just called it a Coulomb branch because there's still an unbroken U1, so it deserves to be called it. And I sort of said that the geometry is special Kähler, but it's not true. It's some refinement of special Kähler, a certain way of tying together hyperkähler and special Kähler properties. And it doesn't have a name, though Antoine Bourget, Mario Martone, and I tried to name it. It hasn't caught on as triply special Kähler geometries. And so we wrote a paper on it. And if you want to see the kind of mathematical definition of what a triply special Kähler geometry is, you can look there.
Okay, thanks a lot.
Sure.
Philip, thank you for an absolutely beautiful talk. So you know better than I that these n=2 4D theories also have links to vertex algebras. So that is Coulomb branches, Higgs branches, all of these things seem to be explainable in some sense, or at least characterized using vertex algebras. So is the same thing known to happen with these n=4 theories? And is there anything special about the vertex algebras in this case?
The vertex algebras are blind to the conformal manifold.
Completely blind.
It's completely blind. It's their big failing. As far as I'm concerned. You can prove that the vertex operator algebras is independent of of any exactly marginal operators in n=2, and therefore also in n=4 supersymmetry.
Okay, but there's nothing special about these n=4 versions of the vertex algebras?
Oh no, there is something special. They have those the n=4 vertex algebras are a vertex super algebras. They have I forget exactly what the algebra is. It's not, but it's some kind of super Virasoro. They contain the super Virasoro sector.
Okay, which we don't normally see for n=2.
Yeah, no, it's not there in n=2.
It's really interesting. Thanks again for a wonderful talk. Much appreciated.
Sure. Yeah, thanks for having me. This was fun.
Can I ask also a final question?
Mm-hmm.
So you mentioned holography in a couple of places, and it's clear that all the fine details of the analysis and all the new structures that you're finding are really at finite m. But can you imagine some ways to use large n gravity duals to understand something about these new results in S-duality?
Well, it's very hard to see how, because usually you think of the let me think about this. Taking, I don't know, taking the large and the Atouf limit, right? Keeps you at is the limit in which you're all your electrically charged states are very light, and all your magnetically charged states are very heavy. I mean, they have a different end dependence. So, okay, I'm not an expert on this. There may be some subtle ways that you can use the holography to give a test of S-duality. There were some papers. I'm thinking Aharoni and Witten maybe, who had some paper on kind of a finite n tests of the ADS-CFT correspondence, and I wonder if those might do the trick. But I think my honest answer is I don't really know. I kind of suspect that it's hard to get for holography to see S-duality. It kind of forces you into the weakly, if you're taking the Atouf limit and keeping lambda fixed, going to n large, you're forcing yourself into the weakly coupled limit or corner of the conformal manifold. So it's hard for me to see how you're going to be able to see something about the global structure.
I'm really ignorant to this, but the only thing I could think about is whether there has been some work in understanding higher form symmetries by using holography or not. It seems like it plays an important role in your analysis. I really don't know whether there is some progress in that direction.
Yeah, there is. Certainly, you can ask about higher form symmetries, and that's another. If you can compute these, then this is another a very sort of robust property of these theories that you can use. I mean, essentially, you can show that two things can't possibly be S-dual if their higher form symmetries disagree with one another.
Thanks.
Sure.
It's great talk.
Thank you. Yeah, thanks for sticking around. Sorry for going over so long.
It was just a great talk. That's why we stick.
Jock, you're muted. So
sorry, can I just ask another question about the connectivity issue of these domains? So when you're looking at, I'm talking about things I don't really know a lot about, but when you're looking at the moduli of Clavier manifolds, part of the thing of Reed's fantasy, I think, is the idea of a conifold transition that you can sort of blow down, deform the geometry in such a way you go through a singular point and you pop out in some other quite distinct domain of the moduli space.
it's often what you see between what I would call a Coulomb branch and a Higgs branch of
that's what I was sort of wondering, like, is there an analog of the conifold? What is the analog of the conifold transition, if there is one?
Well, I don't know the answer to the question, but maybe this is the analog of conifold.
Yeah, that was my immediate reaction.
Exactly. Here, the conifold, conifold transition was in higher. This would be a very simple example because I just got a one complex dimensional and a one complex dimensional space, and so calling it's nothing nearly as complicated as a conifold transition.
But
would be some analog of that. And in general, when you're not in n=4, where you have these nice sort of negative constant curvature geometries here, there is some complex geometry on the conformal manifolds, and it satisfies some interesting kind of requirements. It satisfies the same sort of equations as this thing that was called topological anti-topological fusion equations.
Chicoty-Baffer stuff.
And that also apparently governs the complex geometry of these of n=2 conformal manifolds. So now, is there maybe if someone knows more about that, maybe there's already a notion of an analog of a kind of a conifold transition in those TT star type geometries, or not? I don't know.
Yeah, that's a good question.
Yeah,
I don't know. I need to look at it.
Who was it who did a lot of this? Papadodimas, I think, was the person who kind of pointed out a lot of this stuff about this. Studied as the geometry of these conformal manifolds.
So what was the name again? I missed it.
Papadodimas, I believe.
Let me.
I'm pretty sure I got that right. I really, but I'm pretty sure this is a while ago, probably in the around 2010 or something like that, maybe, or even earlier.
Okay, yeah. I mean, Chicoty-Baffer is really quite old.
Oh no, and Chicoty-Baffer is much further. Papadodimas is the one who pointed out that the relationship between the Chicoty-Baffer and that it applied to the geometry of these conformal manifolds. That's what I'm So he was studying precisely this question that we're talking about, the geometry.
Okay. I didn't know that. I'll have a look. Any other questions from anyone? I think Gabrielle. Well, if not, let's thank Philip again. And Philip, we won't keep you up we need to
I have another meeting in half an hour. I actually have a bunch of collaborators in Korea, so it's like
Right, okay, yeah.
All the time.
Oh, fair enough. Okay, so we're not interrupting things.
Yes, right, exactly.
Yeah, very good.
Okay.
Yeah,